Okay, we're about to start the portion of chapter 11, which is on infinite sequences and series. We're about to start the portion where we test series to see if they're convergent or divergent. So section 11.3, 4, 5, 6, 7 is all about just different methods of testing series to see if the series is convergent or divergent. Now, you might be wondering what the purpose of this is, in particular, since this channel is more for non-math majors. It seems like testing a series just to find out if it's convergent or divergent is something that, unless you're a math major, you won't really do that. And in particular because, so in general, the idea is we start off with a series like this. So in your respective field in practice, in some situation, you come up with or you have a sequence. So you already know the sequence, the A sub n, and most likely you have a sequence formula. So you've got this sequence, but then you want to think about the corresponding series for that sequence, which in the most general form is represented like this. You could just take the sequence that you already know and put it into a summation. This is where you start. Okay, now what we've talked about is that ideally, every single time you're in a situation like this, where you've put your sequence into a summation, ideally every time you would be able to find the S sub n formula for this series, the partial sum formula, to where that S sub n is valid for all n from the start point to infinity. That's ideally what you do, because once you've got that S sub n, then when it comes to analyzing the series, you're home free. You just take the limit of that S sub n formula as n goes to infinity, and whatever that limit is will tell you if the series diverges or converges. It'll tell you if it diverges, it'll tell you how it diverges. If it converges, then the limit is equal to the infinite sum. However, in general, for most general series like this, it's difficult or impossible to get that S sub n formula. We were able to do this for certain types of series, like the arithmetic series, the geometric series, and some of those telescoping series, but those are special cases. In general, even with mathematical induction, you won't be able to find the S sub n for a series that you have. And so with that, again, you might be asking, well then, as a non-math major, why do I care about just analyzing a series for convergence or divergence? If I know I can't get the S sub n formula and find out what the sum is, then it seems like that's only something a math major would want to do, would want to continue on and see if the series is convergent or divergent. Why do I care as a non-math major? Well, actually, there's a very good reason why this is something we definitely care about as non-math majors. Okay, and so think about this scenario. So you have your series, you have a sequence that you've put into a sum. So you've got this series. You realize that you can't find the S sub n. And so next what you do is you use one of the methods that we're going to learn in the upcoming sections to test the series to see if it's convergent or divergent. Let's say you determine that it's divergent. Well, in that case, you know that you can't use it as a sum, as an actual sum. It diverges. It doesn't equal, the sum doesn't equal to anything. Okay, now, but let's say you determine that it's convergent. You determine that for sure it's convergent. Well, in that case, you know that it's actually a usable series. The sum actually has a meaning to it, like with a number for the sum that you can use. Okay, well, as a non-math major, what you would do is, so yes, you can't get a formula, an explicit formula for the S sub n with just like a function of n. However, if you notice, okay, you have this, right? Well, what is this? Well, okay, well, this is the infinite sum, but we can rewrite it this way. Change n to I, a sub I. Right, if you have this, then you have this. We're just changing the notation here. What is this? This is the partial sum. Now, it's not in an explicit function of n where you can take the limit, but this is the partial sum, right? If you want to sum the first 5 terms, then you write out the first 5 terms and you sum them up, the first 5 terms of the sequence. You plug in n is equal to 5 here. Okay, so what you can think about is that since you know that this converges, you could go to a software like MATLAB or any kind of coding software and make a while loop for this sum and evaluate S of n for like n is equal to 5 million. And you would get a very accurate estimation for this. You can't get the exact value, the technical exact value from a math perspective, but if you put in n is equal to 50,000, if you put in n is equal to 5,000, it would be extremely accurate. But with a computer, you could put in 5 million. And from an applied math perspective, that would be plenty of enough accuracy. Okay, but notice though that if you were going to do this, you would definitely want to, but before doing this, you want to test the series to make sure it's convergent first. I mean, yes, you could always write out this S of n here for the first 50 terms and just visually look to see if it's converging or not. That would probably you'd get the right answer doing it that way. But you probably want to get an official answer to say 100% it's convergent based on a convergence test. Then once you determine it's for sure it's convergent, then do this. Okay, now so since it is of interest in a lot of scenarios to calculate partial sums this way when you can't find the infinite sum, but you know it's convergent, that's the purpose of remainder estimates. So like the R sub n that we talk about, the R sub n of an infinite sum, that's the remainder. You've got the S sub n, the partial sum, and then everything else that's not included in the partial sum is the R sub n. For the different types of tests for convergence, like the integral test, the comparison test, the ratio and root test, we talk about different ways of estimating what the remainder is. And it's valuable when you can do this because what you can think about is if you had like a code written for a partial sum, then instead of inputting the n value that you're going to calculate the partial sum to, if you're able to do a remainder estimate for that partial sum, then you can input a percent of accuracy that you want your partial sum to be within of the actual sum. And then with that percent accuracy, the code would calculate the corresponding n that the partial sum needs to be added to. But even if for some reason you were able to determine that a series is convergent, but you couldn't come up with a remainder estimate, I think there's situations where it just doesn't work. It works out to where you can't even come up with a remainder estimate. Still, I mean, it's still valuable to be able to, you can always, if you verified that the series is convergent for sure, then you know that the sum is actually meaningful, then you could just go input n is equal to 5,000 or 5 million or whatever. And even though you can't say for sure what exactly the accuracy is, it's still very useful to be able to say officially if a series you have is convergent or not.